Hey YouTube, how's it going? Yak Science here with another organic chemistry video. If you haven't watched the previous video on SN1, the concepts, I'd recommend that. This video is going to be dedicated to just problems, right? Problems that you might see on the test and possible tricks that the teachers can throw at you. So I encourage you to pause the video before I solve the problem because I'm just going to jump straight into them, okay? So let's take a look at the first one. MEOH is just shorthand for methanol. Okay, so what's going to happen? We have a leaving group. We know leaving group leaves is the first step, but we also have an opportunity for rearrangement. So we have a hidden hydrogen right here that we haven't drawn in. So we're going to bring that hydrogen over here as the leaving group leaves, one step, right? That way, instead of getting a secondary carbocation, we get a tertiary at this position, okay? So what that leaves us is this. Carbocation right there, because that hydrogen now moved to this position. We have some nucleophile, some methanol floating around in solution. It's going to attack right there at the carbocation. What we end up with is something like this. But now we have oxygen with 3 bonds. That has a positive formal charge. So how do we fix that? Deprotonation. We're going to deprotonate using another methanol. Grab that hydrogen, send the electrons over to the oxygen. And remember your double arrows because it's acid-base chemistry. That'll get us to our product. Okay, so it'll look something like this. Okay. Not necessarily the best way to draw it, but you know the teacher will know what you mean. So sorry about that. But that's the answer. A lot of people will just put the OCH3 over here, and don't get me wrong, that is a product in the real world. This product will form, and the product without rearrangement will form. Remember, it's just probability. It's whatever's most stable. So this would be the major product. The other product without doing rearrangement would still occur. If they wanted all products, you would have to include the one without rearrangement, okay? Let's move on to another example. Okay. That's a pi bond, sorry, it's a little unclear. Okay, perfect. Let's react this with some ethanol. Another very weak nucleophile. Cannot do SN2, but it can do SN1. By the way, I forgot to include heat in the last step. I hope you caught that. Sorry about that. In the last example, I should have put heat because remember you need heat for the first step, the leaving group leaving. Okay, first question you ask yourself when you're convinced that you're doing SN1, is there room for rearrangement? Now, if we have the carbocation here, it'll be secondary. Here, it'll be secondary, and here it'll be secondary as well. So is there rearrangement? The answer is yes, because the number of carbons attached to the carbocation is not the only factor that determines carbocation stability. The closer you are to an alkene, the stabler the carbocation. So a secondary here is less stable than a secondary here, so we will do rearrangement. There's a hidden hydrogen, there's 2 hidden hydrogens right there. Right? We'll grab one of them, move it to this position as bromine leaves, and now we're ready to start. Okay? We know exactly where our carbocation is going to be. It's going to be, and it's kind of ugly, sorry about that. It's going to be right here. That's our carbocation position. We have some ethanol floating around. That's ethanol. Going to attack the carbocation, and then of course our favorite step, deprotonation, is coming up. So we have oxygen, hydrogen, ethanol, positive formal charge because oxygen has 3 bonds. Use another methanol to deprotonate it. Easy peasy. Sorry about that. That's an arrow going to oxygen. Remember your double arrows. And that'll get us to our product. Okay, it'll look something like this. that's your ethanol attached. Okay, ethyl group. So that's the answer. Remember again, the product without rearrangement will form as well, but that would be minor compared to this product. The closer you are to an alkene, the better. So another problem. Okay, so first thing, let's react it with some isopropyl alcohol. Shorthand is IPROH. Isopropyl alcohol just looks something like this. Okay, it's another weak nucleophile. So we know we're dealing with SN1 territory, or E1, but we haven't gotten there yet. So here we go. Can we rearrange? That's the first question we asked. Well, this is tertiary right here, and there's no possible alkene or getting closer to resonance or anything like that. So we're fine here. No rearrangement. So what happens first? Let's add some heat. What happens first? Leaving group leaves. So now what do we have? Okay. And now we have the CH3. I'm not going to give it stereochemistry because now the carbocation is really sp2 hybridized. It won't have stereochemistry, so to speak. It's sort of pseudo sp2. So I'm just going to draw the CH3 like that. Okay. Now we have some nucleophile hanging around in solution. So let's do it like that. Okay. Isopropyl alcohol. It's going to attack at the carbocation. So that leaves us here. We still have that wedged methyl. And I'm not going to include stereochemistry yet. I'm going to include it in the end because remember, we have a racemic mixture with SN1. We're going to have some that are inverted and some that are retained. So I'm just going to draw that at the very end. For now, I'm just going to keep it 2 sticks. Okay. We need to deprotonate. So we'll get another isopropyl alcohol to do that for us. Here we go. Take that hydrogen, electrons go there. So now we have to, double arrows, we have to take account the fact that this is SN1 and there's a racemic mixture. Will this stereochemistry ever change? No, because it's not the attacked site. So the attacked site is either inverted or retained. So let's draw our 2 products. Here's one product, wedged methyl, and let's draw the retention product first. So this is where stereochemistry is retained. You'd have a O. Like that. That's kind of bad. Isopropyl alcohol, wedge, and you're going to have this product. Sorry, I'm running out of room a little bit. Wedge, but this time, the reverse stereochemistry, right? S comes to R comes to S. It's the reverse. Hopefully you see that. I think you do. And so I really like this example because you really have to deal a lot with stereochemistry. Let's react that with some ethanol. Heat. So first question, weak nucleophile, we're dealing with SN1. Can we do rearrangement? We actually have to, because otherwise we're forming a primary carbocation, and that's a big no-no. So can we move any hydrogens? The answer is actually no, because this is a quaternary carbon. There are no hydrogens to move. So we cannot form a quaternary carbocation. That doesn't make sense, okay? So we're going to have to do a methyl shift, just like a hydride shift, but we're going to move an entire methyl group. So we're going to move this entire methyl group over here. Very common. And now what we have is this. I'm going to sort of rearrange, and bromine leaves, forgot to include that. I'm going to sort of rearrange this molecule to look better. So 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, perfect. And what's going to happen is the carbocation is now here. Okay. New position is tertiary, it's happy. We have ethanol. That's a weird way to draw ethanol. Okay. attacks carbocation, we get something like this. But now that oxygen has a plus formal charge, because 3 bonds, use another ethanol, excuse me. Take that hydrogen, deprotonate, and we're good to go. Okay, good stuff. Okay. Let's react this with methanol and heat. So we have actually a couple options here. We have a primary carbon, so we can't just kick off this leaving group. What we need to do is rearrangement. So we could bring this hidden hydrogen right here. We could bring it up and then form the carbocation right here, tertiary. We can also do the barn door, which we learned about in the last video, which basically involves breaking this 5-carbon bond and moving this to bond with this carbon, but that would lead to a secondary carbocation. So will it happen? Yes, but the tertiary is far favored, so we're going to do that. We're going to move this hydrogen up to the carbon as this bromine leaves. That gives us a methyl group actually on top, CH3, right? It gains that hydrogen. And now we have a carbocation right here, tertiary. That's a plus sign, sorry. So now we have methanol come in, attack the carbocation. So we have a methyl group over here. We have an OH-CH3. That needs to be deprotonated by another methanol. Double arrows because it's acid base, and then we have our answer. Okay, good stuff. So that's SN1 in a nutshell. It is more complicated than SN2 because there's a lot more to consider. Remember to consider carbocation stability. Remember to consider where the carbocation should be ideally. Remember to include heat, and remember to deprotonate if necessary. And one last thing that I forgot to mention, I should have said this earlier, so sorry about that. In terms of ordering the most stable to the least stable carbocation, taking into account resonance and tertiary, secondary, primary, this is the order that is typically taught. Your teacher may change it around because some of these are actually kind of debatable and depends on the situation. The general trend is this: tertiary with resonance, more stable than secondary with resonance. Secondary with resonance is more stable than tertiary without resonance. So if you're ever in a situation where you could rearrange to either get tertiary without or secondary with, go with the secondary with, okay? That could be a pretty tricky situation. Tertiary without resonance is more stable than primary with resonance, but primary with resonance is more stable than secondary without resonance. And then obviously primary without resonance is the worst carbocation. It'll basically never exist in nature. So use these as a tool. A lot of times on tests, teachers could ask you, which of the following reactions will happen fastest? And they'll present you one that's tertiary versus one that's primary. And you'd have to know that the tertiary would happen fastest because the rate determining step, remember, is based on how stable the carbocation is. So thanks for watching.